So good morning, everyone, and welcome to today's class. In the last class, we looked at the OLS, and we looked basically at the OLS in the context of simple linear regression. And we looked at various concepts there, which I'm not going to repeat. Now, when it comes to multiple regression, this is just a generalization of what we did in the simple linear regression case. Remember the word simple in what we were discussing last week. Simple here just means we have two variables, where one of the variable is the independent variable and the other one is the dependent variable. If you have more than two variables in your model, then you say that you have multiple regression. So multiple here means that we have more than two variables. We have more than two variables. And in the context we are looking at, one of the variable is the dependent variable. One variable is independent variable. Then two or more are the independent variables. So that's what we call multiple regression. And in our case, we shall be looking at multiple. So in our previous class, we looked at simple linear regression. So in this case, we are just discussing the linear case. Then now in this class, we're going to discuss multiple linear regression. So we shall be assuming some linear relationship in the between the variables of interest. Okay, so I'll start by giving a general format of the regression model or multiple linear regression model. Then after that, we'll use the OLS method to estimate the parameters involved in the question, or the betas, and so on and so forth. So let's start by saying that the general linear regression, we are calling it general because now we are not restricting ourselves to just one explanatory variable. We are not restricting ourselves. We can have as many as possible. We can have as many we can have as many explanatory variables as possible. So we're saying that the general linear regression with k explanatory variables, is just an extension. Of the simple linear regression, as follows. It's just an extension of the simple linear case that we looked at last week. So the regression equation is yi is equal to beta naught plus beta 1 of xi. Sorry, let's say this is x1, not xi, of x1 plus beta 2 of x2 plus all the way to plus beta k xk plus ui. So that's the general linear regression model. So what we were discussing last week is just a special case of this equation when the number of explanatory variables is 1. So what we were discussing last week is just the same equation, but now we didn't have all these explanatory variables. We just had this part and this part. Okay. So then the interpretation here of the regression coefficients. So again, we note that the parameters beta naught, beta 1, all the way to beta k can be estimated or will be estimated using the OLS method. But there's a slight difference in the way in which we interpret the regression coefficients. There is a slight difference in the way we interpret the regression coefficients. So we say that because if you differentiate this function with respect to each of the, if you do what you call partial derivatives of y with respect to each of the independent variables, generally you will get this general equation, because the partial derivative of y divided by the partial derivative of xi, where I takes the values, i's are these subscripts, so I can be 1, 2, 3, all the way to k. So the partial derivative of that will give you the beta j. So for instance, if you take this equation here, you differentiate with respect to x1. You differentiate with respect to x1. It means that you are going to hold all the others constant. So you'll assume x2, x3, all the way to xk are just constants. So their derivatives will all go to 0, and you'll be left with change in y with respect to x1 will just be beta 1, And the same case, if you differentiate this function with respect to x2, then it means that you will hold x1, x3, all the way to xk constant. And the partial derivative will be, the partial derivative of y with respect to x2 will be beta 2. So that's why I'm putting the subscript here. Okay, so I can say for I starting from, so I and j are starting from the same place. So for I starting from 1 all the way to k, and the same case with j, a to j, I mean to k, like that. So you can have bit. So this value here takes either beta 1, beta 2, all the way to the end. Okay. Then we say that the coefficients beta j. So these are the coefficients I'm calling beta j, beta naught, like that, especially from here, especially the slope coefficients, not the intercept. So the coefficients beta j indicate the marginal effect. They indicate the marginal effect of variable xi, and they indicate the estimated change in y, the estimated change in y for every unit increase, in xj, in xi, for every unit increase in xi, when all the other factors, or when all the other variables, let's say that when all the other variables or factors are held constant. In our first class, we introduced the concept of ceteris paribus. So that's what we are applying here. So when you're interpreting the effect of a given regression coefficient here, for instance, if you want to interpret the effect, if you want to interpret beta 1, you will say that beta 1 is the change, either increase or decrease, in the value of y for every unit increase in x1, but when you are holding the effect of the other variables constant, when you hold the effect of x2, x3, all the way to xk constant. So you interpret the effect of one variable when you are holding the effect of all the other variables or factors constant. So that's still the same concept as a ceteris paribus. Okay. All right. So we say that we just note that multiple regression. We just note that multiple regression opens up. Multiple regression opens up several additional options, several additional options to enrich the analysis, to enrich the analysis and make modeling more realistic compared to simple regression. So if you remember in our previous class, we looked at, we attempted to predict the wages using only educational level or the number of years spent in education. And as you saw, even from the R squared that we obtained from that regression, it was very small. It was very small. We were just getting around 16% of the variation in the wages as explained by the number of years in education, as far as the data that we're using is concerned. So you find that a simple regression model was quite limiting, because it means that in that modeling, there were more than 83% of the variation in the wages that was explained by factors which were not captured in the model. So now when you use a multiple regression model, now you are able to allow more factors to be at play in the modeling. And that will give you a more realistic prediction of the variable y, or the dependent variable in this case. Okay. So that's just a note. That's just a note. Then I want us to move to the estimation of the regression coefficients. I don't know whether there is any question. Okay, so now we move on to the estimation of the regression coefficients for multiple regression. And the concept behind this estimation process is just the OLS, If you remember, in the case of simple linear regression, after applying the concept of OLS, we came up with two normal equations, which we were able to solve simultaneously and obtain the values of beta naught and beta 1. So in this context, we shall also be obtaining some normal equations, which after being solved simultaneously will give us the estimates of the regression coefficients. And we are saying that for the sake of illustration, as you know, when you talk about multiple regression model or multiple linear regression model, we can have so many explanatory variables as long as there are more than two. So you can have 2, you can have 3, you can have 10, and so on and so forth. But for the sake of illustration, we shall consider a multiple linear regression with only 2 explanatory variables. For the sake of illustration, we shall have a model with 2 explanatory variables. But as we've seen, when you use your computer, like for instance, when you use Excel, you can run a regression model which has more than 2 independent variables, okay? So for the sake of illustration, we are doing this. So let's consider this model. So y is equal to beta naught estimate plus beta 1 estimate of x1 plus beta 2 estimate of x2 plus u estimate. That's a population regression function, the estimate of the population regression function. Okay, so the corresponding normal equations are the corresponding normal equations are, and I want to recap a bit of how the normal equations were obtained in the context of simple linear regression. So let's put this one on hold. Let's put this one on hold and recall that in the case of simple linear regression, we had this function equal to beta naught plus beta 1 like that plus the estimate. Okay, so from here the sample regression function was y hat is equal to beta naught plus beta 1 hat x. Okay, and then the normal equations were, in this case, so this is the population regression function, and this one is the sample regression function. So the normal equations I know we obtained the normal equations using differentiation, but now this is a quick way of knowing how the normal equations are coming out. So when you have two variables in your model, and in this case we have two variables, that is x and y. Okay, when you have two variables, you will end up with two normal equations. So that means when you go back to our case here, because here we have three variables, that is y, x1 and x2. Of course, I'll write down the estimated value of y. Then we expect to have three normal equations. So if you have a model containing 10 variables, including the dependent variable, then you'll have 10 normal equations, and so on and so forth. So let me show you a quick way of coming up with the normal equations in the simple linear regression case. So the first normal equation is given by, you take this function. Remember, at some point, remember in the background, you have some data, because these estimates of beta naught and beta 1 are estimated from some data. So you have some x and some y somewhere. So here we have x1, x2, and we're assuming the size of the sample is xn. So we have n values of x. And then we also have all the way, we have n values of y. So what we do, we sum up. So when you talk about, if I were very strict on the notations, I'll be having a y and I here, okay? But I'm choosing to keep it simple like that. So here, so that means even here I have a y hat, okay? So I have y hat 1 like that all the way. So what I do, I need to sum up this variable, the values of this variable here, y estimate. So I need to sum up them. So that means y at 2 all the way to y at n. I need to sum up these values here. And when you sum them, you will get summation of y hat. So for simplicity, I'll just call it summation of y, okay, and so on and so forth. So so in this case, for simplicity, I'll just keep it like that. I'll keep it like that. So the first normal equation is given by summation of y. The first normal equation is given by summation of y is equal to, then you sum this item here. So for simplicity, I'm considering this equation plus beta 1x. I'm considering the equation like that. Okay. So so I'm going to sum, in this case, I'm going to sum the y's. So I'll have this summation here. So I need summation of y. Then I need to sum this value here. Sorry, I need to sum this value here. So I'll be having a beta naught here, and it will be appearing here. So I need to sum beta naught plus beta naught plus beta naught plus all the way to the nth one, which is beta naught. So I'll be dealing with something like this. I'll be having beta naught plus all the way to plus beta naught. And how many values are these? So they'll be equal. The number of beta naughts is equal to the length of the data. So I'll be having this, the first one, the second one, all the way to the nth one. So if I sum them up, I'll end up with n beta naught. I'll end up with n beta naught. Then plus, you come here, you sum up this item also. You sum up this item also. Okay. So when you sum that up, you'll get beta 1 summation of x. And that's your first normal equation. That's your first normal equation. The second normal equation, number 2, is obtained by, you take this equation here, then you multiply every term by the independent variable. That is x. You multiply every term. So this is one term, another term, and another term. You multiply each one of them by the independent variable. So you have xy is equal to beta naught x plus beta 1 x squared. Then after that, you sum up. You sum each term after multiplying. So you will end up with summation of xy is equal to, when you sum this, you get beta naught summation of x plus, you sum this, you get beta 1 summation of x squared. And those are the two normal equations that we obtained from the previous class. Those are the two normal equations in the case of simple linear regression. So we'll use the same concept to come up with normal equations for any number of independent variables. Okay, so now back to our regression equation. So now back to our multiple regression equation. So we have already given this kind of function. So I'm going to consider this function up to this point. I'm going to leave out the error term. So we consider in multiple linear regression with two explanatory variables. Let's consider this. Consider this equation, y is equal to, this one should be estimator. Even here I should have put estimator, but it's okay. It's still okay. So here you should be having the hearts like that. So plus beta 1 estimate x1 plus beta 2 estimate x2. So if there were more variables, I'll continue like that. But we said we shall illustrate using 2. So here we need, because we have 3 variables, y, x1, and x2. So we have 3 normal equations. So here we have 3 normal equations. And we shall be obtaining them using the same analogy. The first normal equation, you sum up every term of this original equation. You sum up. And remember, you have a sample of size n. You have a sample of size n. So I sum up this one, I'll get summation of y. Then I sum up, these are constant. This, by the beta naught is a constant. So something like a 2. So you are adding 2 n times. So you 2 plus 2 plus 2 all the way to the nth time. So that's why you see we are just bringing an n, then beta naught estimate. When you sum up that, so you will not get summation of beta naught. You will not get that. You will not get that. Okay. Then the second, the next term here you have plus. You sum up this term here, you get beta 1 estimate summation of x. Then the last one here will be beta 2 estimate, this x1 summation of x2. So that's the first normal equation. That's the first normal equation. Now the second normal equation, just like we did in the case of simple linear, you take the first independent variable. The first independent variable, which is x1, multiply everywhere by that. So you'll have y x1 is equal to beta naught x1 plus beta 1 x1 squared plus beta 2 x1 x2. So that's what you have. Then you sum. So when you sum that, you'll end up with summation of y x1 is equal to beta naught summation of x1 plus beta 1 summation of x1 squared plus beta 2 summation of x1 multiplied by x2. So that is your second normal equation. Then your third normal equation, now we work with the second independent variable. The second independent variable, which is x2. The second independent variable, which is x2. Multiply everywhere in this equation by x2. So that means you'll end up with y x2 is equal to beta naught estimate x2 plus beta 1 estimate x1 x2 plus beta 2 estimate x2 squared. Then you sum. So you'll end up with summation of y x2 is equal to beta naught estimate summation of x2 plus beta 1 estimate summation of x1 multiplied by x2 plus beta 2 estimate summation of x2 squared. So those are the three normal equations that we need to solve so as to obtain the estimates of beta naught or beta 1 and beta 2, or the regression coefficients. So if you had three independent variables, you will continue like that. You will continue like that. So you take the first independent variable, you multiply everywhere, then you sum. And the other normal equation will be you take the second independent variable, multiply everywhere, then you sum. You continue like that until you are done with all the independent variables. But the first normal equation, as you've seen, you just sum up the terms of the original equation, you sum them, and you know that you are summing them, each variable, where each item here represents a variable, will be summed up n times because the size of your sample is n. Any question there? Let me know if there's any question there. So these normal equations are just linear equations. They are linear equations, and they are linear in beta naught, beta 1, and beta 2. So these are just linear functions of beta naught, beta 1, and beta 2. They are linear functions. They are linear functions. So that means that if they're linear functions, you can solve them the way you solve simultaneous equations. So here we have three simultaneous equations which can be solved using any method. Using the elimination method, you can use the substitution method, you can use the matrix method, either the Cramer's rule or the matrix inverse method. Okay, so let's note that solving the above equations simultaneously. Solving the above equations simultaneously yields the estimates of parameters beta naught, beta 1, and beta 2. Please notice that I've not used the hat here. So whatever you get from solving this function here is what will be the estimates, is what will be having the hat. So it's also good for you to note that from this equation here, or from this set of equations, these values here, these are got from the data. So you just need to go to your data here. You have x and y. So you had x1. Let's say you have x1, x2, and then you have y. You just need to go to your data and sum up this. So here, for instance, you need summation of x1. So you add up the data that is given there. Then here you need to sum up x2. So these summations here are not unknowns. The only unknowns here are these guys here. These ones. Even n, the number of observations, is known. Okay, so that's why I said it's a function of these three, beta naught, beta 1. So it's not a function of x1 and x2. It's a function of beta naught, beta 1, and beta 3. And it's linear because, as you can see, the powers of beta naught, beta 1, and beta 2 in all the equations is 1. So they are all, the three equations are linear functions. So all this information will be given. All this information will be given. So you just need to find the values of, so the unknowns here are beta naught, beta 1, and beta 2. Okay. Then we note that there are various methods of solving the above system of linear equations. You can solve the above system of linear equations using various methods, so we just list them, but the details, I think you know. You can use elimination method. You can use elimination method. You can use substitution method. it may not be easy for you to use a graphical method. You can use the matrix method. The matrix method here, you have the matrix inverse method, or you can use the Cramer's rule. The Cramer's rule to find to solve the system of linear equations there. Okay. So we'll not go to the details there because those are things that we've covered in other classes. Okay. So now I want us to move to the decomposition of the sum of squares and also how to obtain the goodness of it. So just like we saw in our previous class, the sum of squares has three parts. We have the total sum of squares, we have the explained sum of squares, and then we have the unexplained sum of squares. So in the same manner, so we say that in the same manner, as with the simple linear regression, we have what we have. I'll start by writing it in words. We have total sum of squares is equal to the explained sum of squares, plus the unexplained sum of squares. Okay, so we can say this is T. Usually I call it like this. SST, total sum of squares, is equal to sum of squares explained. Sometimes I prefer to use the word because of what I mentioned last week. There are some people who use SSE. There are some others use SSE to mean sum of square due to errors. Okay, but here the errors, we are not calling them errors in our case. We are calling them residuals. So sometimes I prefer to have it in that way, in this format, so that there is no confusion. Explained plus sum of square due to residual like that. Remember, the residual is sometimes called the error. So sometimes if you use SSE to mean SS due to the errors, somebody might confuse it with the sum of square explained. The same case, the residual is also the regression sum of squares. So if you use SSE, SSR to mean the residual, somebody might use SSR to mean the sum of squares due to regression, while the regression is the explained variation. So to avoid confusion, I'll keep it like that. So using the formula, we said that this is given by summation of, if you take y minus y bar squared, then this is equal to summation of brackets y hat minus y bar squared, then finally plus, this is the error. Isaac, I can see you have a question in a minute. Plus summation of y minus y hat, like that. That's the residue, like that. So that's how you break down the sum of squares. So Isaac, I think you have a question. So that's the difference between the different versions of y. So we have y, the plain y is the observed value. Usually that is the data that we have collected. Then we have y bar, which is the mean of y, which is obtained using this formula. It's a very common formula. Then y hat is the predicted, or the estimate of y, So once you've estimated the values of the regression coefficients and you are given the independent variables, then the predicted value of y, or the value of y that you obtain from the given equation or the regression equation, is what you call the y hat, or the predicted value of y. Okay, then we say that now we are back here. So we say that this information can be summarized. This information can be summarized in a table. A table called the ANOVA table. The ANOVA. ANOVA stands for analysis of variance. The analysis of variance table, the ANOVA table. And the ANOVA table, this is something that you've seen when you use Excel to analyze data. Usually it provides 3 tables, where the first table shows the descriptive statistics or some of the descriptive statistics, as well as R squared. Then there's a middle table there that shows, or that's called the ANOVA table. And then the last table that shows the regression coefficients. So the ANOVA table looks like this. We have 5 columns. We have a table which has 5 columns. 1, 2, this is 3, 4, and 5. So the ANOVA table will look like that. We have the 5 columns, but sometimes we have 6 columns, where the last column can be capturing the p-values. But for now, we don't need them. We can be computing them later. So the first column is the source. The source. In other words, what is the source of the variation that we are talking about? And I want us to have an equation like this in mind. So in the case of multiple, so let's have something like this. Beta naught estimate plus beta 1 estimate x1 plus beta 2 estimate x2. So there are 2 sources of variation here. We have this variation, so we have this part, then I can have the error term there. So we have this part here, which gives us the y hat. That's what gives us the y hat. So this is the regression part. And then we have this, what you're calling the residual part. So variation in y will come from this part plus this part. So we are breaking down the source. So this is one source and the other source here. So we're breaking the source into 2 parts like that. Then we have what we call the degrees of freedom, and the degrees of freedom under the regression part here is equal to the number of regression coefficients, which is k. So the number of so this should be the number of explanatory variables, which is k minus 1. So this number here, the degrees of freedom here, is just equal to the parameters beta 1, beta 2, all the way to beta k. All the way to beta k. Okay. Then you minus 1. You minus 1 there. Then under the residuals, we have n, which is the size of the sample. Size of the sample. Then you minus k. You minus k. So here, the type of variation under the regression, so the type of variation that we find under this part of the model is what we call the explained sum of squares. Sum of squares. So this is what we're calling SS explained. And then the type of variation we have down here is the unexplained sum of squares, or the residual sum of squares. The residual sum of squares, which is equal to, which we denote at SS resid, like that. And now the next column is easy to obtain because we just say it is the mean. So in this column here, we talk about the mean of the sum of squares. So here we have the mean. We need the mean of this item here. The mean of this item here. So these are already sum of squares. So we know that the mean is given by sum of something divided by n. So in this case, we'll have the mean sum of squares. The mean the mean sum of squares explained. So the mean of this, the mean of the explained sum of squares will be given by SS explained divided by the degrees of freedom. Sorry, divided by k minus 1. Divided by k minus 1. Divided by these degrees of freedom there. Then down here, we have the mean sum of squares of the residuals. Down here, we have the mean sum of squares of the residuals. The mean sum of squares of these, which will be given by sum of squares resid divided by the degrees of freedom corresponding to that, which is n minus k, which is equal to that. Which is equal to that. Okay. Then from the expression above here, from this kind of expression here, we have already captured this. This is the explained. This is the explained sum of squares. This is the unexplained sum of squares. So that means when you combine the two, you'll get the total sum of squares. So we can have another column, another row here, which we can have it like this. We can just have it like that. So the table can stop there. Then here we can have the total sum of squares. So now you just sum whatever is in each column. You sum whatever is in each column. So you take this k minus 1 plus this, you'll get the answer is n minus 1. If you add up those two, you'll get that. So this is the end of the table here. Then when you add this, you'll get sum of square explained plus sum of square unexplained, or the residual. When you add that, you get that. Actually, you don't add that because it doesn't make sense. Then finally, we have what you call the F-statistic. The F-statistic. And this is the statistic that we shall be using to check the goodness of fit of our model. To check the goodness of fit of our model. And the F-statistic, maybe I should mention this. If you look at this formula here, let me write it in as a formula. So the mean sum of square explained, remember, is given by this, the explained sum of squares, which is given by this formula here, y hat minus y bar squared. So this is summation of y hat minus y bar squared. That's the explained. Sorry, this is the explained. So we're saying that the mean sum of square explained is given by this guy over k minus 1, where of course the numerator here is the explained sum of squares, like that, divided by the degrees of freedom corresponding to that, divided by k minus 1, divided by k minus 1. So you'll notice that this is some variance. This is some variance. So this is the explained. This is like the explained variation, which you can replace this word with a variance. The variation in y that is explained by the model. So this is a type of variance. And then this also is another type of variance. It's also a type of variance. As you can see, these are formula for variance. Basically, we know that the variance of x is given by summation of x minus x bar squared over n minus 1. So this is some type of variance. The same case with the other term here. So when we talk about the F statistic, we talk about the ratio between these two variances. The ratio of these two variances. The mean of sum of squares, those are variances. So the F statistic here is given by the mean sum of square explained divided by the mean sum of square residual. So these are ratio. We are dividing two variances here. If the mean sum of square explained is equal to the mean sum of square residual, if the two parts are equal, then you will get a ratio equal to 1. In most of the cases, if the model is fitting well, you will find that the mean sum of squares explained is always bigger than the mean sum of squares residual in most of the cases. The explained part is always bigger than the residual. So we expect the ratio to be always greater than 1. If the model is nice, we expect it to be greater than 1. Okay. Though if the model is not very good, you might find that you have the ratio being less than 1. So that means that maybe you have left out so many variables in the model, or so much is not explained by the model. Okay. So we have this F statistic here, which will be given by that ratio. So that's the statistic that we shall be using later on when we go to testing of hypothesis to check how good the fit is. Okay. Let me know if there's a question there. Okay, so let's move on. So we can say that where K is the number of parameters, estimated. And when you're given a model like this, you notice that this model here has 2 explanatory variables. So, and there are 3 parameters that have been estimated. So here we have estimated beta naught, beta 1, and beta 2. So in this case, K is equal to 3. In this case, K is equal to 3. And we are always using K minus 1 because we want to leave out one of the parameters that does not correspond to a variable, the beta naught. So that's the logic behind that. So we're having K minus 1 as the degrees of freedom, but K is the number of parameters that have been estimated in that model. Okay, then N is the sample size. Yeah, I think that's important. So we need to note those two, that K is the number of parameters, and then N is the size of the sample, or the number of observations. Then what we're calling MSS explain, and MSS recede or residual are the explained and unexplained variances. You notice I've used the word variance, variances respectively. Then the F statistic is the ratio between this is the ratio between these two variances. Is the ratio between these two variances, and we say that the objective is to check whether the ratio is greater than 1. Of course, we say in a significant way. So when you talk about is this checking here is the same as testing. Is to test whether the ratio is bigger than 1 in a significant way. So that calls for hypothesis testing. You cannot just find that by just looking. You need to test hypotheses about that value. Then we say that we hypothesize. We say that we test this hypothesis. We test this hypothesis by comparing the F calculated, that is above. The F in the table up there is what we're calling the F calculated by the F critical, which is read from, let me put brackets like that, which is read from F distribution tables. I know you've come across the normal distribution tables and the T distribution tables. We also have other distributions known as the F distribution tables, which are used to test hypotheses revolving around the comparison of variances. If you want to compare variances like the ones we have here, then you use the F distributions. Then we'll go to the details of how to use the F tables a little bit later, because you need to have, you need to set up a critical region and the acceptance region. Then you compare the calculated value and the table value and the critical value to check whether you are going to reject the null hypothesis. And the null hypothesis here is that the variance explained and the variance unexplained are equal. So to test that hypothesis, you need to follow some steps, which we'll be discussing later on in the next class. Okay, then we need also, we need two sets of degrees of freedom. We need two sets of degrees of freedom. That is the numerator degrees of freedom, and the numerator degrees of freedom will be given by these. The numerator degrees of freedom will be given by this. So if you look at the mean sum of square explained and the mean sum of square residual, you notice that each one of them has a divisor. Each one of them has a divisor here. So these divisors correspond to what we are calling the degrees of freedom, because this is what goes to this is our numerator and this is our denominator. And the denominator has this divisor and the numerator has this divisor. So those are the degrees of freedom in each case. So we have the numerator degrees of freedom, which is given by k minus 1, and denominator degrees of freedom, which is given by n minus k. So later on, when I show you the F tables, you will see that there are degrees of freedom for the numerator and degrees of freedom for the denominator. So we'll be looking at those details a little bit later. Okay, and then this F statistic here will perform mainly the work that is done by R squared in the case of simple linear regression. Okay, so the F statistic will also tell us how good the fit is. Okay, any question there? So in modeling, there are two types of problems that you can come across. There are two specification problems that you can come across. So we have what we call the overspecification and underspecification. Now, when you talk about the overspecification of a given model, this is when you include so many variables. You have so many variables in the model, some of which maybe are not very important in the model. So when that happens, if you look at a model like this, y is equal to beta naught estimate plus beta 1 x plus beta 2 estimate x2 plus like that, plus the error term. It's always like that. So all the way to x beta k xk, like that. So if you have so many variables, including some variables which are not important in the model here, then you will notice that the degrees of freedom for the explained mean sum of squares will be increasing. And that means that the numerator degrees of freedom will be increasing, and the degrees of freedom for the denominator will be decreasing, because this is given by k minus 1. So as you increase the number of explanatory variables, then k will grow. And then when you minus 1, there might not be so much difference. Then you notice that the degrees of freedom for the denominator will be n minus k, where this is very large. And remember, in almost all the cases, we recommend that the sample size is always bigger than the number, let's say is bigger than the number of explanatory variables. So you find that as this one grows, you find that this one, the entire of the degrees of freedom here goes down. So that will affect the ratio that we called there, the F statistic, because the F statistic is given by the mean sum of square explained divided by the mean sum of square unexplained, or the residual. So this is where you have the, so here we have divided, so here we have something like this. We have the, here we have the explained sum of square divided by k minus 1. And then here we have the residual sum of square divided by n minus k. So if you play around with this, you notice that this is the same as explained sum of square divided by k minus 1, then divide by this, which becomes n minus k over the residual sum of square. So we are saying that this number here becomes very large. This one becomes very small. And that means that your f will become very small. That means that your model is likely to be insignificant, okay? Or to be less significant, if I may use that word. It will be less significant compared to a well-specified model. So that is how over-specification affects your model. And you find that the effect of over-specification is not as harmful as the effect of under-specification. Where on the other hand, under specification, this is a scenario where either you have completely omitted a variable that should be in your model, you leave it out completely. Or maybe the variable is captured in the model, but in the wrong format. For instance, instead of capturing x squared as one of your variables, as one of your terms, you capture it as x. So you find that the effect, which was to be captured by x squared, is left out. So that's what we call under specification. And this one will affect your predictions more than over specification. So under specification is a more serious problem than over specification. And for more details, you can check the class notes or the slides. Now at this point, I want us to have some exercise, to have some example, so that we can see how to obtain the various, especially how to obtain the various terms in the ANOVA table, unless there's a question. So let me write down the question. So here is the question that or the example that we want to solve. We're given some scores of some 6 randomly selected students, and then we are required to do the following, okay, shown there. So now we can solve this question. We can let the call GPA, for the sake of convenience, let that one be denoted by Y. Then high school GPA, we can let that one be denoted by X1. Then SCT, let that one be denoted by X2. Okay. So we need to fit a linear regression model to predict Y given this information. So we need a linear regression model. We need a linear regression model of the form Y is equal to beta naught plus beta 1 x1 plus beta 2 x2. We need something like that. We need a model of that format. Okay, so our objective is to find the estimates. So the normal equations, the corresponding normal equations are, so the first normal equation will be summation of Y is equal to n beta naught plus beta 1 summation of x1 plus beta 2 summation of x2. Then the second normal equation will be, now we'll be multiplying by x1 throughout. So we have summation of y x1 is equal to beta naught summation of x1 plus beta 1 summation of x1 squared plus beta 2 summation of x1 x2. And number 3 The third normal equation, we take x2, multiply everywhere, then we sum. So this will be summation of y x2 is equal to beta naught summation of x2 plus beta 1 summation of x1 x2 plus beta 2 summation of x2 squared. So those are the normal equations. Those are the normal equations. So from the data, we need to obtain those summations. So let me copy the data here again. Let's do this. Let's obtain the summations in Excel to make our work a little bit easier. So I'll put the data in Excel and I'll be getting the summations from Excel. That will make my work a little bit easier, even multiplication. So having this data in Excel will make our computations a little bit faster. So from the first normal equation, I need summation of y. I need the number of observations, which I know is 6. I need summation of x1. I need summation of x2. So I can just come to my Excel, then I just sum these values. I just sum them like that. I'm using the auto sum like that. And I also sum this auto sum like that. So those are the values I want to take to the other side, 17.8. So from the first normal equation, so substituting, we have summation of y, which is 17.8, is equal to n. N is 6, so we have 6 beta naught. For simplicity, I leave out the heart. I can just keep it. So we have 17.8, 19.5 plus 19.5 beta 1 plus 14.4. Sorry, this is 144. This is 144. 144 beta 2. So that's our first normal equation. As I told you earlier, these values are known. So the only unknown are the beta naught, beta 1, and beta 2. So that's our first normal equation. The second normal equation, we need summation of, we need y times x1. We need y times x1. We need x1 squared, and we need x1 times x2. So going back to Excel, we can obtain those values. So here I need y times x1. I need y times x1. I need x1 squared. So this is a table that we shall use to obtain the various summations. So, and we are interested in the totals, the summations, the ones in bold. So back to our whiteboard. So that's our first normal equation. And the second normal equation will be summation of y times x1. And we saw from the other side, this is 58.3 is equal to summation of x1, and summation of x1 is 19.5, and 19.5 beta naught plus x1 squared. This is 64.55 and 55 beta 1 estimate plus x1 times x2. X1 times x2 gives us 469.7, sorry, 0.7, 469.7 beta 2 estimate. So that's our second normal equation. And the last normal equation will be given by summation of y times x2. This will give us 426.9, which is equal to the summation of x2, which is 144 beta naught estimate, plus x1 times x2, which is 469.7 beta 1 estimate. And finally, we have beta 2 summation of x2 squared, and this is 3470 beta 2. So these are the simultaneous equations we are talking about. These are the simultaneous equations we are talking about. So you can solve them using elimination method, using substitution method. You can use matrix method. I don't know which method you propose we use in this case. Which method is easier for you? So using the Cramer's rule, let's consider two simultaneous equations or two linear equations with two unknowns. So we have A11 x1 plus A12 x2 like that, where x1 and x2 are the unknowns. X1 and x2 are the unknowns. Okay, so this system of linear equations can be written in matrix format like this. You can have it like this. This is similar to what you call this is A, and this is X, and this is B. The objective is to find the value of X. So using the Cramer's rule, we use some quotient of some determinants. So this vertical, so we, for instance, if we want to find the value of X1, will be given by this is a determinant of this number of this matrix. So you replace the first column of this matrix A, you replace the first column, this is your first column, this is your second column. So you replace the value of the values of the first column with the matrix B. So you have B1 and B2, then the second column remains. Then divide by the entire matrix A. So this is matrix A. This is matrix A without changing a thing. Then the value of X2, will be given by the determinant of. So you replace the second column of matrix A with matrix B, or with the column vector B. So you keep the first column the way it is, and you replace the second column with B1 and B2. Then the divisor does not change. So it's the same in both cases. Then you find the two determinants, and you find the determinants, and you divide, you'll get the values of X1 and X2. So these vertical lines, they stand for determinant of whatever is between the two lines. So if you have a 2 by 2 matrix, the determinant is quite easy to obtain and is given by, so we can say, for instance, if you consider this matrix here, which is a 2 by 2 matrix, assume it is non-singular, then determinant of A, which is sometimes denoted by this, is given by the product of elements in the leading diagonal, minus product of elements in the other diagonal, or in the lagging diagonal. For instance, if you have a matrix like this, if this is your matrix A, then your determinant will be given by, or can be denoted by this or that, or you can even have it like this using vertical lines. And this is equal to, you take this product, which will give you 8, minus product of elements in the other diagonal 21. So the determinant in this case is minus 13. When you have a system of linear equations with 3 unknowns, for instance, if you have these, if you have A11 x1 plus A12 x2 plus A13 x3 is equal to some constant there, A21 x1 plus A22 x2 plus A23 x3 is equal to some constant there. Then you notice that when you have 3 unknowns, you need at least 3 equations. So A31 x1 plus A32 x2 plus A33 x3 equal to B3. So in matrix format, you can convert this into, so you have A11, A12, A13, A21, A22, A23, A31, A32, and A33. That's your matrix A. You multiply that by this vector, x1, x2, x3. So that should give you B1, B2, B3. So in matrix format, we have it like that. So once you have it like that, using the Cramer's rule to obtain the values of x1, x2, and x3 will be quite simple. Remember, in our problem, what we are trying to solve will not be having x1, x2, and x3. Instead, we shall be having beta naught, beta 1, and beta 2. So that's what we shall be having in this context. And here we shall be having some constants, some numbers, and these are also some constants. So this one is known, this one is known, this one is unknown, this one is unknown. And this is what we are trying to figure out. Okay, so if you want to use the Cramer's rule, you will use again a quotient of some determinants as shown below. So if you want to find the value of x1, will be given by the determinant of, again, let's consider these three columns. So we have three columns in that matrix A. So this is our matrix A, this is your X, this is your B. So in matrix A, you replace column 1. And you notice that column 1 contains the coefficients of x1. Column 1 contains the coefficients of x1. These guys, so these are the coefficients of x1, as you can see there. So you replace it with b1, b2, or b3. So this will be b1, b2, b3. Then you copy and paste the other columns of matrix A. So we have a12, a22, a32, a13, a23, and a33. So you find the determinant of that divided by determinant of the entire matrix A. Let me just call it like that in short. Determinant of this matrix A, the one we're calling A. So when that will give you the value of x1. Then the value of x2 will be obtained in a similar manner. So you will have x2 will be given by, now you replace column 2 of matrix A with matrix B. So you will end up with, so column 1 remains a11, a21, a31, b1, b2, b3, then a13, a23, and a33, like that. Then you divide by determinant of matrix A. Determinant of matrix A. Then x3 will be obtained in a similar manner. So x3, so you replace the last column with this vector. So you have the determinant of this a11, a21, a31, a12, a21, a22, then a32. Then here b1, b2, b3, determinant divided by determinant of matrix A. Determinant of matrix A. Okay. Then how do we find the determinant of such a matrix? So we can use a shortcut method. There are two methods. You can use the method of minus, which will be very long, but you can use another method, which is a shortcut method, to obtain the value of the determinant. Okay. And I want us to use the example that we have, the problem that we have, to find the determinants, then we solve the question. So the question that we are solving, the simultaneous equations can be written in matrix format as shown here. Okay, so these are estimates. So now from here, we need the value of beta naught estimate, which will be given by, so again, here we have, so this is similar to our matrix A. This is our matrix A. This is our matrix similar to X, which we are calling betas now. This is our matrix B, like that. Okay. So the estimate of beta naught will be given by, so again, let's notice that we have columns like this. We have columns like this. So beta naught, remember these values here in the first column were the coefficients of beta naught. These are the coefficients of beta 1. These are the coefficients of beta 2. Beta 2. So the numerator here, so we are going to have the determinant of 17.8, 58.3, 426.9. Then I copy the other columns, 19.5, 640. This is 64.35. And that is 64.35. 64.35. Then we have 469.7, 144, 469.7, then we have 3470. We have that determinant divided by determinant of the entire matrix A, which I'm going to write in full now. We have 6, 19.5, then 144, then 19.5, 64.35, then 469.7, then 144, 469.7, then 3470, like that. So that will give you, so you find the determinant of the numerator, determinant of the denominator. Then the value of beta 1 estimate will be given by, I now replace the second column of matrix A with this vector B here. So I'll have the determinant of, so the first column remains 19.5, 144. And now here I have 17.8, 58.3, and 426.9. Then finally here I have 144, 469.7, 3470. That's the numerator divided by, for simplicity, let me just call it determinant of A, which is the same as these. And we do the same for beta 2. We do the same for beta 2. Let me write it here so that all of them can be seen. So beta 2 estimate will be given by, now I replace the last column of this matrix, this column here with this column. So I will have the determinant of 6, 19.5, 144. Then we have 19.5, 64.35, 469.7. Then now I'm having 17.8, 58.3, and then 426.9 divided by determinant of matrix A. So the divisor will be obtained just once. You just obtain the divisor just once. So I want us to compute we have a few minutes remaining. So I want us to compute the determinant of A. Then once you get the determinant of A, using the same concept, you can obtain the determinant of the numerators. Okay, then now from there, you just get the quotients and you are done. So let's deal with matrix A. So let's find determinant of matrix A. So determinant of matrix A will be given by the following. So you copy the matrix A the way it is. So you have 6, 6, then 19.5, then 144. I'm copying the entire matrix, 19.5, 64.35, 469.7, 144. Then we have 469.7, that 470. So once you do that, usually you can put a line there. Then you copy and paste the first two columns next. You make the first two columns the next two columns here. So you have a matrix now containing 5 columns. So you copy these two, you paste them here. So you have 6, 19.5, and this is 144. Let me remove some of these things so that they don't confuse me. So I have the first two columns down here, alongside here. So you have 6, then 19.5, then you have 144. In the second column, 19.5, 19.5, 19.5, 64.35. Then we have 469.7. Okay, so you have a matrix which seems to be having 5 columns, where these 2 columns are just a duplication of the first 2 columns. Then let's do this. Starting from the main diagonal of the original matrix. So let's highlight these. highlight the first these elements, the main diagonal like that. Then on the right hand side, you'll find that you can obtain another diagonal like that. Then you can obtain the final one like this. Okay. Then assuming that those are three parallel diagonals, you find the product of elements in every diagonal. So you take this times that times that. You also take this times that times that. And you take this times that times that. Then you add up those products. Okay. So the first thing, so here the determinant of A will be given by, I'm multiplying the elements in each diagonal. So I have 6 times 64.35 times that 470. I hope that is correct. Huh? Then that plus the product of elements in the other diagonal, so 19.5 times 469.7 times 144. And I add the last one, 144 times 19. This is 19. Oh, this one should be 19.5. Huh? 19.5 times 469.7. Then please notice that after you do that, you put brackets like this. So you sum them to get a single value. That's not the determinant. Huh? So then you say minus what you get there, minus, you do the same for the other diagonal. You do the same for the other diagonal. So let me use black. So starting from this diagonal here, then on the right, we have another one to avoid mistakes there. Then we have the last one there. They are not very aligned, but they should be parallel like that. So we do the same. So this one minus. So again, I get the products, then I sum them. So this will be 144 times 64.35 times another 144 plus 469. This is 469. 469.7 times another 469.7 times a 6 plus that 470 times 19.5 times 19.5 like that. Then remember we have a bracket like that. So the determinant of A is some item here minus some other item here. I think we have calculators, so let's try to multiply this a little bit fast. We see what we're going to get. So the determinant is 81.36. That's the determinant of A. So that's the divisor. That please notice that we have corrected here. This is 64.55. 64.55. We have corrected that everywhere. Okay, like that. So that's the divisor that will be put down here in the three estimates. Then quickly, let's do the numerator here. Let's very quickly do the determinant of the numerator for beta 1. Then you can compute the others after the class. So let's do that. So we want to find the determinant of the numerator of the estimate of beta naught. So we find the determinant of the numerator here. We have the denominator already. So determinant using the Cramer's rule here. So this will be given by, so we need to take to have this matrix, we copy the next the first two columns. We copy the first two columns to have it to have this expression looking like this. So I just remove this line here. Then I just copy these two. So we have 17.8, 58.3, 426.9, and here I have 19.5, 64.55, and 469.7. So I can find the determinant there. So starting from the main diagonal, So I'll be talking about this one. Then we have this. Then we have this is 144, and I love that. So this is so a determinant will be given by 17.8 times 64.55 times that 470. Take that plus 19.5 times 469.7 times 426.9 plus 144 times 58.3 times 469.7. So we take all that brackets there minus, this is minus the other, on the other side we have this, we have that, and then we have this minus, so we have 426.9 times 64.55 times 144 plus we have 469.7 times 469.7 times 17.8. These are plus. Then another plus 3470 times 58.3 times 19.5. Then remember we have brackets like this, like that, and we'll get the determinant of that term. We'll get the determinant of that value. Maybe you can quickly do it so that we can get the estimate of beta naught. Then you finish the remaining part at home. Okay, so the determinant of the numerator in the estimation of beta naught will be given by that 269.493. Then the estimate of beta naught will be given by that divided by that, which is 3.31. So you can finish the remaining part. So beta 1 estimate and also beta 2 estimator after the class. So you will also finish the remaining part of the questions. You are supposed to find the R squared, the multiple R squared, the F statistic. Then you repeat this analysis using Excel. Then we can compare notes when we meet in class next week. So that marks the end of today's class. Have a nice weekend.